Hey everyone, welcome back to another OSCP journey video. I know it's been quite a minute. We had a whole lot going on, but I promise I haven't been twiddling my thumbs the whole time. If I sound a little weird or if I'm sniffly or coughing, I'll do my best to edit those pieces out, but please kind of be patient with me if anything slips through. I'm just recovering from the flu, kind of doing my best over here. So with all that said, we're going to get started on binary exploitation today. We're only going to go through maybe 1 or 2 challenges. I was trying to be a bit ambitious and go through like 5, but realistically there's just not enough time to do that in just a single video. But with that means we have a lot more content coming. So yeah, I recently noticed also that we have around a little over 2,000 subscribers on the channel now. Thank you guys for subscribing. That is super awesome. If you're enjoying this content, please drop a like and hit subscribe, all that kind of standard YouTube jazz. Like I said, I've always noted this as more of a vlog than an educational series, but the fact of the matter is that I am walking through things, and it is kind of tutorial like, even though most of the videos are you guys just watching me suffer. But there are a couple of POCs and stuff like that I've demonstrated. So since that is educating and helpful, or maybe you just like the process, I don't know. I say I don't know what the appeal is. I know exactly what the appeal is, because this is the kind of content that I seek out on the regular. Creators like Live Overflow or Rook or IPSec, just showing their processes are super helpful, and I hope that mine has been helpful for you guys as well. So won't drone on that any longer. Let's dive right into it. So today we're going to go through some of the let me get this window over here, the exploit education exercises. So like I said, we're doing binary exploitation now. We're going to start small though. I want to make sure I understand everything and I'm conveying it in a correct manner. I've already done the challenges that we're going to go through today, so it's not going to be quite as live as some of my others, but I'm also very, very inexperienced and very, very new to these things. So hopefully this is just going to help me sharpen my knife, so to speak, sharpen my workflow in doing these challenges. So my hope is to start with stack 0 and maybe get up to stack 2 today. We'll see about that, but we'll definitely be starting the stack 0. I can tell you guys I've been all the way through stack 6 already. Yeah, I don't think I've done stack 7 yet, but I've done some ret to libc stuff. I feel like I've got a pretty good grasp on it, and to kind of show you guys where I'm at and what I've kind of built up and what you'll see in this video. I'll be referencing this off to the side very frequently. This is a little binary exploitation GitHub repo I've got going right now. It just contains some notes, but I will put any goodies that I learn along the way here. But if you just need some notes or an example workflow to start as your baseline for your personal workflow, this is mine. So I established so far, I've only really done Linux stuff. We'll get into some Windows stuff after, I guess kind of after I'm super comfortable here. To be honest though, when it comes to binary exploitation, Linux and Windows, it's not really all that different. Well, I haven't done a lot of Windows exploitation personally. I do know that the hardest part is going to be getting used to the different debuggers and different kind of reversing environments. But with things like Cutter, Radare, Immunity, all that kind of stuff, it's not necessarily that it's hard, it's just different. But the principles that you'll see, the kind of general broad workflow that you'll see me kind of do, is always going to be the same. You're dealing with assembly, you're dealing with the same vulnerabilities. If I compile one program that's vulnerable to buffer overflow, it's written in C, and I compile it on Windows and I compile it on Linux, it still has the same buffer overflow vulnerability. The difference is that I've got to reverse it and figure out addresses that things are going to now have, because they will be different, and I'll have to modify my exploit to account for those differences. So overall, everything's very translatable from what I understand. Now, there does get some complicated steps in there when you start considering things like ASLR, DEP, all these kind of modern protections we have. It is my understanding that when it comes to the OSCP, those things aren't really expected of you. You're not going to be expected to perform even a known ASLR bypass, because it gets really complicated and complex, and it defeats the purpose of what you're learning when it comes to binary exploitation. All of those techniques are far more advanced, but that's not to say they're not relevant. I feel like they probably fit into the OSC. I really don't know much about the OSC, but that they are certainly more advanced, especially when you're tackling this from the perspective of first-time reverse engineering and doing binary exploitation. That being said, that doesn't mean you won't be expected to work in an environment where maybe ASLR is enabled, but maybe a binary has been compiled to ignore specific things. There's all kinds of potential variances that you could encounter. I really don't know what's going to be on the OSCP, but I'm kind of approaching it from the perspective of what I've kind of read and what I've been told, that this is going to be very basic buffer overflow stuff. Now, with that said, even basic buffer overflow stuff requires a good solid workflow and a good understanding of what you're doing. And so a lot of times what you'll see here in this video today, since we're doing Protostar, we already have a work environment kind of going for us. But when it comes to binary exploitation, you want to emulate your target environment as close as possible. So say you get on the OSCP, or say you're on an actual engagement and you find a mysterious program that's proprietary. Maybe you have some source code for it. Maybe you're actually auditing this program. Who knows? But it's on a system, and you've got to write your exploit and do all your development on a system that is similar, because if you don't, you're not going to get certain addresses won't match up. You're not going to get the right architecture, right kernel. There's a lot of differences between even different Linux distros. So say you're targeting a Ubuntu 32-bit VM, you need to do your exploit dev on that Ubuntu 32-bit VM as much as possible. So that's kind of what I'm focusing my personal workflow on towards. But it's important to remember that while we do have a lot of modern protections on different operating systems, these skills are still very relevant when you consider different ways developers might compile things for certain reasons that they may not realize are not secure. And then even more simple than that, embedded systems. We have lots and lots of embedded Linux and Windows systems that have to remove security features as a compatibility constraint because they cause a lot of overhead, and you need to run finely tuned systems. And as a result, while a buffer overflow may exist in, say, I don't know, Apache, say there's a ODay for Apache that's a buffer overflow that would never ever work on any other systems because of the modern protections, it would work on an embedded device because, like as Vis would say, totes my goats, put a web server on everything. So put a web server on some embedded Linux device, and it's vulnerable to some Apache ODay, then yeah, that one actually would be relevant. So these techniques don't go away. They are basic, they are fundamental and foundational, but that's why they're important to know. So that's those fundamentals, building that strong foundation, and that's why it's really good to practice all these things. And once you start getting into CTFs and stuff too, you'll be able to solve some cool challenges with this knowledge. So I didn't really think there's any reason to defend that. I just wanted to put that out there, so maybe people who don't have any experience that think, well, why would this still be relevant? That's why. I just wanted to kind of throw that out there. I'm not gonna have this page kind of up much longer for the duration of this. I'll come back to this page a little bit just to kind of show the source code before we start on each challenge that we do. But I did just want to kind of put this here because I will be referencing it off to the side. With that, let's start with stack 0. So our goal here with each of these, for every single one of these, when you get on the Protostar box, they're going to be a set UID binary, and the goal would be to pop a shell, get root, because by popping a shell with a set UID binary, you're going to have the root group permission set, which will give your shell root privileges. So you'll be running as root. So it's all of these are targeted at local privilege escalation. We're going to SSH into the box as user with the password user. Those are the defaults for Protostar. But the reality is, for every single one of the exploits, you'll notice we have gets buffer, and the buffer is 64. And same thing here, same thing here, same thing here. The exploit code that we would write for this would pretty much be the same, with a kind of a variation in address every time whenever we're pointing it at our shellcode. So that's why what's great about these is they're all challenges that help you build up to that shellcode. So we're not going to just start off by writing shellcode. We're going to solve the challenge for each of these, and we may not even get to actually writing shellcode today, and that's okay. We need to understand what we're doing and how we're manipulating data in the program before we jump straight into writing shellcode. All right, so I'm going to show you guys kind of how I do things. So I've got this little working directory kind of going here. I'm going to remove that precompiled program. You notice I had that exploit pi. This is what a working exploit would look like if it was actually working. I was actually developing this for another custom challenge I had written for my local DEF CON group. This exploit code doesn't work, so if you're attending our meetings, sorry. It's close, but no cigar. It's not going to give you the answer, that's for sure. But a lot of exploit code pretty much looks like this, and I'll break it down a little bit now, but we'll go into more depth later. But the idea is you're going to overflow it with a certain amount of bytes, and you're going to, at the end of everything, put a target address, and this is where you're going to want your program to redirect code execution to. So by putting so many bytes in on the stack, you're going to put this address on the stack, and the return pointer is going to return that address, which means, hey, I'm going to return this address, go execute whatever's at that address, and from there you want shellcode and stuff like that. A lot of the exploits in exploit exercises, or for Protostar anyway, are going to really only require overflow and target address at first, until we get to the shellcode. Then we start getting knobs and all that kind of stuff. So we'll explain more about that once we get there, but just kind of want to show that since it was in the directory. So I've already got the source code for stack C here. We're actually not on the Protostar VM right now. This is going to be one that I'm going to show some of my own personal workflow with before we hop on the VM. So let's compile stack 0. And you'll notice even that when we compile it, it tells us that gets is a dangerous function and should not be used. So go GCC. So for actual exploitation of this to be relevant, we would have to compile this with stack being executable, and we'd have to disable a lot of the protections that are on my local system here. I am running a modern version of Kali, which I believe still has system protections enabled, stuff like that. But this is a basic buffer overflow. It's going to still allow us to segfault and overwrite stuff in memory. We just really won't be able to write an exploit to jump anywhere. So no shellcode, but we still will be able to modify the value, which is the point of this challenge. And so this is a good way to identify buffer overflow. So we're going to be introduced to some very, very basic fuzzing, and also just take a look at how code flows around and where stuff goes in memory. So if we run stack 0 and just type in a bunch of crap, it tells us to try again. But one very basic fuzzing thing I like to do is just throw a crap ton of A's at it and see what it barfs out. So we're just going to smash A for a little while, hit enter. You've changed the modified variable segmentation fault. Great, we're done. On to the next challenge, right? Well, actually, technically, yeah, but we're actually going to dive in a little bit closer here. So I use Radare a lot. It's like GDB, and I was trying to say it's like GDB and Ida had a baby or something like that, which is kind of true, but really, Radare is its own animal. It's really hard to use, and it's really complicated, which is why I took a whole bunch of notes on it, so I know exactly how to use it every single time, because it is so stinking powerful and so worth the learning curve, in my opinion. So we started with TACD, which starts with the debugger mode, so it has a debugger built in, so we don't have to use GDB. We'll seek to sim.main, which is our main function. We'll analyze everything, so it's going to analyze all the function flags, etc. We're going to print the disassembly. So we're going to print the disassembly of the main function. What this is going to let us do is grab the top address for main, and also just see if print out what we're working with. DB, we set a breakpoint at that address, so we're going to set that breakpoint there. And just take a look at the code. Since we've already seen the C code, we already know how this kind of works. So we're moving value of 0 into EAX. We're going to check what the heck EAX is and jump to a specific address. If we jump to here, it means that we failed. If we fail this check, it means that we have changed the modified variable, and we'll be able to go to the end. So yeah, super cool, right? Already right away kind of see what's going on. Now, if you didn't have the C code already, this would also be kind of hard to figure out what's going on with no assembly knowledge, but you can at least see the call to gets, so you know where the vulnerability is, as long as you're familiar with gets being a bad function. And then you can also see just the general test conditions. But what's really cool about Radare is we can jump into visual mode. Ooh. 2 capital V's. And this gives us a control flow graph, which will break down that conditional even more and just kind of help us figure out how the hell this program's moving. So we're going to run it by hitting colon and DC, and we hit our breakpoint. We can display our registers with DR. Right now there's nothing in there because the program just started. So now we'll step through this with Shift capital S. So this isn't really meant to be a Radare tutorial. I'm just trying to be helpful so you guys know what I'm doing on the keyboard. We see we have RIP here. This is actually going to tell us where we are at in program execution. That's our instruction pointer. So we're stepping through, and we're going to step through till we get to that gets call. And now we've got to throw a bunch of stuff at it. So I'm actually going to throw a pattern of the alphabet at it. So I'm going to do like 4 characters in a row till we get to Z. So AAA, BBB, CCC, and so on. Alright, and the reason I do this is because it's going to be way easier to identify what value overflowed. So if we did want to write an exploit for it, we would know, hey, if it failed at the last R, which means we can chop off this R and I just added a bunch of junk. We can chop off this R and write the rest of our payload in there, right? So you guys will kind of see where I'm going with that. So we'll enter that. And then we'll move on here. So now we do test EAX, and we jump down to that conditional we were expecting, which means we have successfully overwritten the modified variable. So let's display our registers and see what we overwrote it with. Looks like our AX is filled with 5 4s. So we did overwrite it. It's definitely not 0. Let's open up Python and see what the heck hex 54 is. So we can do CHR hex 54. It's T. So we overrode it with a bunch of T's. So if we were to remove all 4 T's, we could actually insert a payload after that and start writing some shellcode and stuff like that. But that is the best example of how we've overwritten the variable. So we've successfully completely changed that modified variable and met the conditional. So this challenge is solved. And that's how the data kind of moved around in memory. So that's going to be our only kind of look at Radare. I didn't want to kind of dive too deep into that. I will do one more thing for you guys that I think is just super duper cool that I want to show. You can do this advanced visual mode, which gives you all kinds of crazy stuff. So you have your standard thing. You can do a debugging through here. So standard disassembly view. While Radare doesn't have a decompiler, it does have this pseudocode kind of generator, which does its best to make C-like code, but this is just pseudocode. It's not actually trying to decompile the assembly back into C. With that said, it does a pretty good job. This is mostly accurate. So it says, you know, if it's not that conditional, try again. Otherwise, you know, keep going through the loop. But it is kind of missing some stuff here, as you can see. We don't even have that other string that we were looking for. But what's really cool is we can see what's going on with the stack, any references, and the register values. I really like this. So you could debug in this view. That's you get there by doing V exclamation points, fancy visual mode. But yeah, I just really like that. I want to show that off. I have this pipe dream of becoming a Radare power user. It may never happen, but oh well. Alright, with that we'll clean up here. That's stack 0. But now we need to SSH into the actual Protostar box, wherever that is. All the cleanup I did. There we go. Alright, we'll give ourselves a bash prompt because it gives us an ugly shell. Alright, cool. So all of Protostar's challenges are located in opt Protostar bin. Now we see everything, and we can actually check those permissions that I was talking about, like I said before. So all of these, every single one of them actually set UID binary for root. So we did stack 0 already. Let's take a look at stack 1. Alright, so stack 1 source code. We've got another buffer. and we need to specify an argument. Okay, so it looks like our goal here, we're going to have to do a little bit of exploit development to get what we want. So we need to not just modify the variable, we need to modify the variable and give it the correct value. So we're going to do this in GDB this time. And our goal is to change the value to this hex variable. All right, so let's do it. If we run stack1 and we don't pass it anything, it's going to ask us to pass something. So we're going to pass it a whole bunch of A's like we did before. And it says try again. You got 414141, which means we successfully overwrote something, but we did not modify it to what it needed to be. All right, so we're actually going to be able to do this particular challenge in a pretty neat way. So I'm going to see if I can do it without GDB at first. So we'll do some basic fuzzing. So we're going to do that same alphabet pattern we did before. I actually got this from IPSec, by the way. I didn't make this up as some grandiose thing. It's just really, really good. Thank you, IPSec. I mean, sorry, not IPSec. I got this from Live Overflow. Whew. Too many contributors to my personal growth and development. They are all amazing, though. Alright, so we're going to pass it all this and see where we land. So 5151, so that's super useful. Let's open a new tab here for a second. Python, chr, 0hex51, Q. So we landed on a bunch of Q's, which means if we pass the same thing in with no Q's and just do P's, we get a bunch of zeros. Alright, so now you think the value we need to enter is this, so we just type that in, right? That'll work. Okay, kind of. It's backwards. It's more than just backwards. It's wrong. It's not even anywhere close to the right value. And there's two reasons for that. One reason is because of Indianness. The other reason in this case is just because we entered something in decimal, and this is its hex representation. Like, it's not even the right value, so we didn't even pass this in as hex correctly. So here's where we're going to do some very, very simple exploit development. So I'm going to kind of go to my home directory, and I'm going to make a exploit1.py. And I'm going to import struct, and I'm going to save this real quick so I don't have to type everything out like an idiot. We're going to copy our good payload string, and we're going to say our buffer, that's what we'll call it, that's a buffer. Our target address is going to be, let me reference my notes here. So struct's really cool because it allows us to pack in and basically convert an Indian, it gives it, it's not an Indian value, a hexadecimal value as if it were basically an integer, and it will handle everything without us having to worry about Indianness or anything like that. So we'll say struct.pack I, and then we'll get that target hex that we want the modified value to be. And then now we have to do is say print buffer plus target address. See, this is already looking kind of like that exploit code that we had earlier, right? So if we say Python, let's rename that first so it look like less of an idiot. So say Python exploit1.py. And go fix our code because we spelled stuff wrong. Struct.pack, I believe. Yes. Just copied it wrong. Alright, cool. And now you see we have this DCBA, which actually, funny enough, is exactly what that hex value goes out to. So if we go to something like ASCII to hex.com. This is a great like converter website. I'll bring it over. So if we go over here and we put in that that hex code 61, 62, 63, 64, get rid of the 0. It just goes to lowercase ABCD. That's all it is. So if we had appended ABCD onto the end of that string, we wouldn't even need this exploit code. But that's what the exploit code allows us to do. And so I'll show both examples of that. But basically, we're going to pipe this out as exploit 1. And we're going to say, actually, we're not even going to, we'll have that there, but we'll just pass it in like we did before. So we'll say opt protostar bin stack 1. And then give it this. You have correctly got the right variable value. So we're able to exploit stack 1 and solve it simply by fuzzing. And that's because it tells us what our values are. We would be able to see the same thing kind of in GDB. In fact, if we look at it this way, we'll say, we'll say opt protostar bin stack 1, and then we'll pass it stuff. Of course it's not gonna let us do that, but that's okay. What we will do is break main and run this with 1. Should do great things. Alright, so we'll be able to say next instruction, next instruction, and I want to go, I have to specify an argument. That's super weird. I thought I did with both of those cases, but guess not. I'm going to Google that just real quick, but I don't want to dwell too long on that since we've already kind of solved that. I just kind of want to show what it looks like in memory stepping through debugger. Pass argument to GDB. Okay, I see what I did wrong. So we're going to pass do this. We'll break it main. So you can see, I say break star main. Whatever. 2 breakpoints. Great. And we'll say run, and that's our argument. So we'll keep stepping through. Alright, so we hit our first breakpoint. And we're gonna kind of examine registers. So we'll say info registers. This will print out everything that's in our registers as of right now. And we're just gonna kind of keep on stepping through. This is GDB Life. We could write a hook. I don't think it's really relevant for right now. I'm gonna say disassemble main real quick, so we kind of get a reference. This is AT&T syntax. So we are currently at 4A2, which is right here. So we're calling that string copy. So I'm gonna go look at that other command. Okay, so this is at this point we should after this instruction we should see the value in our register change, and we do. So it was going to EAX. Alright, just so a reference so no one's lost. We ran the program, we stepped through a couple of the instructions and print out the register values a couple times. Pay attention to, as we step through, we're going to different addresses. Once we got here, I printed the disassembly and saw, hey, we're calling string copy. What let me know that that was a good place to check the registers again is looking at the source code. String copy is actually where we copy argv1 into the buffer. Argv1 is what we passed in. And so at this point, something should have converted to that value, and modified should be represented by EAX if I am thinking about this correctly. So I'm kind of looking for a move instruction. Let me set my disassembly flavor real quick. I joked about it, but it actually is so much better So this symbol main again. Alright, that's way better. So I was trying to see where we're actually setting EAX initially to that 0 value. It would actually be right before. Be like one of these two lines or something. So it's not exuberantly clear, but that is where we actually did that is actually where we can see in memory our value being written. Now, why does that happen? Well, string copy is another one that ignores the fact that the buffer only has 64. It was only allowed 64 bytes, and we're copying over everything anyway. So whatever gets left over will get pushed out. So after 64 bytes, which was around, what did we say? Q. PQ. So at the last P we had, it said no more. We're just going to copy the rest out into the next available slot in memory, which was modified, and we have tacked onto the tail end of that value those 4 extra bytes, which are the lowercase ABCD, which modified it to the correct value. All right. So that's a little bit of us starting to get our kind of bearings and workflow in GDB. We wrote kind of our first basic little simple, real simple exploit. Let's go on to stack 2. So stack 2 gets real cool, and we'll actually write some more exploit code for this as well, because we have a new address we need to hit. And this one isn't just letters that we could pass in. We actually need that exploit code this time. But the vulnerability here is actually the same. We have that same string copy. We have the same amount of bytes. So we actually might not even need to kind of feel around and fish for our payload string, that buffer string. We should be able to use what we have. We'll see. But what's interesting here is that we need to have an environment variable set, because the string copy is pulling from the environment variable. So we'll need to set this greeny value to that variable. So let's look at how we would do that. So we've got our current exploit code. So we'll copy exploit 1 pi, and we'll copy it to exploit 2 pi. Since it'll be a little bit different, we've got to modify some stuff. So let's go ahead and modify our exploit code here. So we'll keep our buffer the same, but our target's new. So our target address that we want to set the modified value to is that. So if we say Python exploit 2 pi, now things look a little bit different. We've got all this white space and weird characters. That's because that hex value doesn't render to anything in ASCII, but it's still there. And so that's what's really important for us to do stuff like this. So now I'm going to write that to a file at exp2. So this is going to be our payload. And we're going to need to set the greeny environment value. So I'm going to export greeny. Greeny is just a custom environment variable that they want us to work with. And we're going to set it equal to, we can't set it equal to exp2 directly. I've got to, how did I do this before? I've got to use some fancy bash. There we go. We'll say cat exp2. And what this will basically do is say, hey, set greeny to whatever this expression evaluates to. And then now when we echo $greeny, which is the environment variable we just set, there you go. Looks like it successfully set to the payload. All right. So with greeny set, we should be able to just run opt protostar bin stack 2, right? It says we've actually correctly modified the variable. So all of our kind of intuitions were correct. The space is the same and all that kind of stuff. However, I do want to kind of show something. I don't think this will work. I could be wrong. But if we run stack 2 from here, no, it still works. Okay, never mind. So we have actually correctly modified the variable. So we'll open this in GDB as well. So GDB stack /stack 2 break at main, and we will symbol main, just to get an idea of where we need to stop. So string copy here is, so we'll set another breakpoint here, make life a little bit easier. So we'll run, we'll continue, and then we'll info registers. Ah, there it is. So step down a couple more and we've got our value that was successfully overwritten in memory. Now where did that actually happen at? So when we did this next instruction in info registers, that was at 4E8, which is, here is that comparison. So we had loaded value in the EX, and alright, cool. Just to kind of validate, we'll keep stepping along. Yep, okay, so that's persistent. Yeah, so that's really all that's to those first 3 challenges. We'll kind of stop there. Or will we? How much time have I spent here? Hell, let's do one more. This one's really cool. I want to do it anyway. Alright, so we'll do stack 4 now. So stack 4 makes us do something a little bit more complicated, and we'll have to modify our payload. So let's go ahead and copy exploit 2 and make exploit 4.py. These aren't really accurate because that last one was for stack 3, and I think the first one was for stack 1, stack 2, stack 3. Oh no, I'm right. Just losing my mind. I picked the wrong one. Alright, exploit 3.py. Alright. So exploit 3.py requires us to do something a little bit different. So let's look at the C code real quick. So stack 3, we have a similar vulnerability as before. We have gets with a buffer 64, but now we have this function pointer that's getting called, and what we're supposed to do is redirect code execution to this when function. And so normally this when function cannot be called by this program. By redirecting code execution, we force it to call that. So that's what our goal is. So let's see if we can't pull that off. Alright, so we don't know where the address is, and we don't know if that link's going to be correct or not. So we're going to have to just start off by doing this in the debugger. And that is okay by me. So let's GDB / stack 3. First, let's run stack 3 just so we have a frame of reference. Bleh. Nothing. And so we'll fuzz a bunch of A's. Okay, so now it actually did something. So we overwrote that function pointer, and it said, hey, we're going to jump to hex 414141. But like that's not real, yo, so we're going to segfault out. That's kind of what's happening here. And in fact, we could fuzz this to a point as well. We could actually take a look at whatever that was in our home folder here. We say wait, any of these. We actually take this and say do a similar kind of fuzzing as before, stack 3. Okay, it looks like at some point our R's actually do overwrite. Let's try that with 4R's, see if it actually goes all the way. It does. Okay, so our payloads are actually going to be reproducible here, but what we don't know is where that target address starts. So let's copy this for now and open stack 3 in GDB. Alright, so we're going to break at main. I'm going to set our disassembly flavored int cell since we're on a foreign box and I don't have this in my config. Alright, so set disassembly flavor to Intel. We're going to run this. Disassemble main real quick. Okay, so we don't know where win is, but we do know there's a function called win. So if we disassemble win, there's the address of the win function right here. Okay, super duper awesome. What we can see whenever we keep stepping through a program here is eventually we'll get to that gets call. There it is. We'll pass this in. We'll keep checking. We'll do an info registers real quick till we see where we actually do overwrite the function pointer. There it is. So we actually do overwrite the function pointer in EAX, but it is not what we it's not the address that we want to set it to. So let's disassemble win again and get that value, because this is what's going to be the key to success for our payload. So let's open up exploit3.py real quick. So that can stay the same, but our target address is actually going to be that of the win function. And so Python exploit3.py, we'll write this out to exploit3, cat exploit3. Alright, so that is going to be our code that should redirect our input. So let's let's opt protostar bin stack 3 and we'll redirect exp3. Code flow successfully changed. Bam. Alright, 3 in a row. I still got it, man. I hadn't forgotten anything I've learned. Heck yeah. Alright, so now I'm going to open this in GDB and do same type of deal. That feels real good. I'm telling you guys, I am brand spanking new to this, so the fact that I'm clinging to the concepts that I've learned so far just makes me ecstatic. I hope you guys, any of you guys that are struggling with this, are able to reach that same point, because it feels great. I don't feel like an expert, but I at least feel like I'm not drowning in what I'm doing. I've got a good grasp. Alright, so we're going to run it and pass that file there. And keep on going till we can't go no more. Just gonna keep stepping through. Check on our registers every now and then. Alright, so we're calling function pointers, jumping to that value. Great. So now if we hit next, EAX was set to the function pointer's value and code flow was successfully changed. Now we can info registers again and it's gone. But the whole idea was to overflow this to that function pointer, and that way when that function pointer returned, it popped this off the stack and said, oh, I know what that is. That's that win function. And we were able to redirect code execution there. Alright, so that really is enough. We'll get to stack 4, 5, and 6 in another video. I don't know when I'll have another video out. It'll probably be sooner than later, since I'm not sick and dying anymore. But I will say this, that probably after the next video, I'll probably be jumping into my OSCP, which means a lot less technical videos and a lot more of those vlog type videos that I was kind of hinting to before, that these kind of already are, but these are more hands-on. But once I start on the OSCP, I'm not really going to be able to share any of it. I'll be able to talk about my experience and share my frustrations and kind of reflect on what I'm learning, but that's probably about it. Yeah, my goal is to get my OSCP by August, but we'll just have to see what happens. But yeah, after the next video that you guys see from me, there may be one or two more, but even with that, I'll probably have started my OSCP, at least started the PWK, not necessarily the exam itself, but I've started the PWK. So that's kind of what we're looking at. It's coming up soon, guys. Again, thank you all for your support. I hope you found this video entertaining, and I hope you saw kind of into my process and what I've learned. I hope I've actually demonstrated that I've learned something that's interesting and helpful for me on my OSCP. That's just more of a note to myself, because when I go back and watch this, and after doing the OSCP, I'm like, good job, me, or you shouldn't have focused on that. You should have focused on this, or whatever. So it's going to be interesting to see. That's the whole point of the series. So, yeah, that is about it. Only other thing, I got a quick plug here at the end. If you're in the Columbus, Georgia area, and you're in need of a DEF CON group, welcome to DC 706. We just got started. We've got our first meeting here soon. Come say hi if you're in the area or want to travel down. We'll have a neat Net King of the Hill CTF that I've got going on, developed by yours truly. And we'll have some Lockpick Village stuff. And I've got our other co-founder, Chris, will be giving a great talk on some malware stuff he's been seeing a lot at work lately. So, yeah, come say hello. With that, thanks for watching.